Welcome to the next segment of High School Geometry with Netz and Weichel. I'm Mrs. Netz,
And I'm Mrs. Weichel.
and today we are covering 2.4 rotations. By the end of the lesson, you will be able to use geometric descriptions of rotations to transform figures and to predict the effect of a given figure. Why do you need to know this? Because you need to be able to understand that two-dimensional figures are similar to another figure if the second can be obtained from first by a rotation. How you will know you know it? When given two similar two-dimensional figures, you can describe the rotation that exhibits the similarity between them.
All right, let's go ahead and get started. We're going to start out today's lesson the same as 2.4. We're going to talk about symmetry. Remember from 2.4, when we were talking about reflectional symmetry, you could flip a figure back onto itself. So if you're looking at a shape, I say close your eyes and I flip it over itself. You open your eyes, you can't tell I did anything. That was when we were talking about reflections. Now we're talking about rotational symmetry, which is when you turn a figure back onto itself. You're going to be turning it around its center, and if you turn it around its center and all the points match up onto any original points, then you have something called rotational symmetry. The way you will find a shape's rotational symmetry is by taking 360, which is one full rotation, and dividing it by the number of sides. Very similar to how you found an interior angle for a regular polygon. So we're going to go ahead and find some rotational symmetry for the following shapes. The first thing you're going to do is take the number 360 and divide it by the number of sides you have. So for the first one, we have an equilateral triangle. So you would simply do 360 divided by 3, giving you rotational symmetry of 120 degrees.
Now, what that means is if you were to take a pin and stick it right in the middle of an equilateral triangle and rotate it 120 degrees, it would appear as if it had not been rotated at all. You could also then rotate it an additional 120 degrees, which would be 240 total degrees, and again, it would look like it had not been rotated at all. Lastly, you could rotate it one more time, making it a total of 360 degrees. And if you'll notice, once again, it doesn't even look like it's been rotated at all. So an equilateral triangle has rotational symmetry at 120 degrees.
And any multiple of 120 degrees.
So 240 and 360.
A square is going to be done the same way. A square we know has 4 sides, so you will take 360 and divide it by 4. If you were to take a square, if you all were to close your eyes right now, I'm going to rotate this square. And now if you open your eyes, you can't tell that it moved, but when I click on it, you can see the green circle is over here on the right side. Same if I go another 90 degrees, you can't tell that I moved it. If I go another 90 degrees, or 270 degrees total, you can't tell I moved it, and then back to the original for 360 degrees. So go ahead and pause the video and find your rotational symmetry for the remaining polygons that we have listed here: pentagon, hexagon, heptagon, octagon, nonagon, and decagon. Okay, so you should have come up with the following rotational symmetries. Regular pentagon is going to have a rotational symmetry of 72. So as Ms. Netz was saying, if you did 72 degrees, but the question was, does the shape have a rotational symmetry of 144 degrees? The answer would be yes, because that would be two 70-degree rotations. For a regular hexagon, the degree of rotational symmetry is 60 degrees. So if the question was, does a regular hexagon have a rotational symmetry of 240 degrees? The answer would be yes, because that would be 4 60-degree rotations, and so on. Heptagon, you should have gotten about 51.4 degrees, and then the remaining 3 go 45, 40, and 36 degrees. And remember, what this means again is that you would turn the shape that many degrees around its center, and all original points would map onto the new points. So a rotation not necessarily around its center, around any other point, is going to look similar to the diagram given here. Please go ahead and fill in the blanks for your next vocabulary word, rotation. It's turning all points of a figure about a fixed point such that every point is both equidistant from a fixed point and all angles formed by the point and its image with the vertex at the fixed point are congruent. So I have an illustration here showing you what that's talking about. The fixed point in which you're turning around is the point that is not moving. It's the center of rotation. When I picture this, I picture our solar system. The sun would be like the fixed point of rotation because it is the not moving piece, whereas all the planets are moving around it. So everything in the world is moving around that center point in the rotation, theoretically. As far as the rest of the definition, every point in the image is equidistant from the fixed point. So what that is talking about is if this point is this far away from the center, it's going to be that same distance when it's rotated. You're staying the same distance always from the center. Like a circle, if I were to rotate this point around 360 degrees, it would be making a circle around that center, all points from a center point. And then the angle that is formed by the point and its image with the vertex are congruent. So what that is talking about is the point and the pre-image point with the center as the vertex is making, in this case, a 55-degree angle. If I were to create that same angle, say from this point and then to this point, it would also be a 55-degree angle. If I were to look at this point and this point with the center point being the vertex, it would be a 55-degree angle. All of those angles would need to be the same. When we're talking about rotations, very similar to our translation lesson, your shape is preserved. In this example, you can see I have what looks like a square is still a square after the rotation. The side length and angle measure is preserved. What I have here, again, looks like a square, so therefore we have 90-degree angles and congruent sides. This looks to be the same size. And then lastly, the orientation is preserved. If this was A, B, C, D, if I rotate it, this is A prime, this becomes here B prime. This goes here C prime and D prime. You can see A, B, C clockwise around. If I start at A and go around this way, it's still A, B, C going around in the same direction. So orientation is now preserved again, unlike reflections. So the only thing that is changing or is not preserved is the position. The location of the shape is moving.
Now, I find rotations actually pretty easy because students understand the coordinate plane. And if you understand the coordinate plane, remembering the rules for rotations is really, really easy.
Agree. We're going right into it. Okay, sorry, I had to see where we were going with this. So I would, if I were you, actually, after we talk about this, I would make maybe yourself a little coordinate plane. I would say this is a very good thing to put in your toolbox when you're working on this. As always, a verbal description is going to just be us telling you exactly what to do. You're always going to know two things. You're going to know the degree and the direction you're going in. Usually the fixed point will be the origin. If it's not, we will also tell you what the center of rotation would be. So in this case, we're saying rotate 90 degrees counterclockwise. The rule we'll talk about in just a second. We'll show you hopefully an easy way to remember your rules. Because we're on a coordinate plane, there will be 3 rules that we'll be talking specifically about. In this case, it's going to be whatever your pre-image xy is, it will become a negative yx. And then notation, notice now the way we decipher between reflections and rotations. Reflections were a lowercase r. Our rotations are an uppercase r, and then the subscript is the degree at which you are turning, rotating. So to remember your rules, you guys have some room off to the left on your notes. I would actually maybe draw yourself a little coordinate plane. It doesn't have to be anything totally fancy. You know that this is quadrant 1 and then from here it goes counterclockwise to 2, 3, and 4. You know that the signs, when I do these, your x and y are both positive. Over here in quadrant 2, your x is now negative, your y, oops, I'm writing the letter y, is positive. Down here in quadrant 3, we are at a negative, negative. And down here in quadrant 4, we are at a positive for x, but a negative for y. So 1 and 3, we have 2 positives or 2 negatives, and then 2 and 4, you have 1 of each, negative x, positive y, and a positive x, negative y. If you understand that, which hopefully you all are good with this, your rules for rotations are going to follow very nicely. I'm going to go ahead and show you on the back side what a rotation is going to look like at first, and then hopefully help you remember an easy way for these. So that leads us into the actual rotation itself. So the first one we have is TURN, very original. We're turning our quadrilateral. So the last 3 lessons, hopefully you've noticed the names of our quadrilaterals. Pre-image, go ahead and graph it, and then push play again, please. Okay, so we're going to rotate 90 degrees. CCW stands for counterclockwise. So I'm going to go ahead and zoom in so you guys can see a little bit more clearly what we're doing. Basically, our quadrant plane is set up into 4 quadrants. So because it's 4 quadrants, it is set up for 90-degree rotations. Remember, a 90-degree rotation can be done more than once. So if I say go 180 degrees, you are going to go 2 90-degree rotations. So every time you rotate, you should be moving 1 full quadrant. If you were to take TURN, which is right here, and you were to turn the entire graph, I ask you right now to take your paper and turn it to the left so that the right side is now at the top. You're going to turn it so it's long ways facing in front of you. What you're going to hopefully see is this. This is what you guys should be seeing right now when you turned your paper. That is the rotation of 90 degrees counterclockwise done for you.
Basically, when you're turning your paper, you're making your x-axis now your y-axis.
Everything is turning around the origin.
And your y-axis is now your x-axis.
What you should be seeing is that the n is right here, so this is now n prime. R at the top right here on yours, when you turned it, you can see that pre-image is now at the top, so this is actually where you're seeing R. And then T down here is rotating over to here. Where am I? No, this is U, I'm sorry. And then right here is our T. So you can go ahead and pause this now if you want to turn your paper back and get these 4 points graphed. I'm going to go ahead and zoom back out, so if you need to pause this to graph these 4 points, please do so. I'm going to now zoom out so I can write in my points. So we can see that T, when I rotated it 90 degrees, is now at -3, 2. We can see that U prime, after I rotated it 90 degrees, is now at -8, 4. R, when I rotated it, is now over here, and it is at -9, 10. And then lastly, N, which was over here at 8, 0, is now at 0, 8. If you look at the connection between pre-image and image, I want you to notice that 2 things have occurred. One, what was X is now in the Y spot. If you don't pay attention at all to your signs, notice that your X's became Y's and your Y's became X's. So you know this rule is going to be written in YX order because they switched places. Now if you look, we started out with all positives. If you look at what happened, all your X's that move to the end are still positive, so none of them change. Remember, the negatives, when we put negatives in our rule, represent a change of sign. That's not happening there. However, your y coordinates, the 3, the 8, and the 9, are all -3, -8, -9 now, so they change signs. So we're going to go ahead and put a negative there. The 0, there is no sign for 0, so obviously that is not going to show that relationship, but hopefully you're seeing it in the first 3. So the rule, the way I like to remember it, if you look back at what you wrote on the other side, look at the from here, go 90 degrees, you're going to go to this quadrant and look at the coordinates. It's a negative positive. Look at your rule. It's a negative positive. So really all you need to remember, the way I remember this, every time you go 90 degrees, XY switches. That's really all you need to remember. If you can just remember that every time you rotate, your X and Y switch. The signs should just fall into place based on where they would fall on this picture. So I'm actually going to give you the rule for 180 first. If you are here and you go 180 degrees, that would be 90 degrees twice. So here's 90, here's 180. If X and Y are switching places each time, here's XY, this becomes YX. Well, if I switch again, it goes back to XY. So I know my rule is XY, then YX. This is going to go back to XY. And then your signs, again, for going 90 degrees twice, are going to be negative, negative. So this is going to be a negative, negative rule. So sometimes students like using the rule a little bit more than the graph. Rotations are a little bit harder to visually see as you're working through them. So T is at +2, +3. The image is now going to be at -2, -3. So why don't you go ahead and pause this and see if you can come up with the rest of this table. Wish you luck, and we'll see you on the other side. All right, hopefully this is how you did. If you're using this rule, we came up with -x, -y. U should have ended up at -4, -8. R should have ended up at -10, -9. And N would have ended up at -8, 0, giving you this quadrilateral over here in quadrant 3. For 270 degrees, you should have figured out or seen the pattern of the rules. Going 270 would be from quadrant 1, here's 90, 180, 270, so YX, XY, YX, and then the rule would be a positive negative rule because of where quadrant 4 is and the coordinates for it. So you're going to switch your X and Y, and then your second number, change the signs. So 2, 3 becomes 3, 2, and then you change the second sign.
Now, notice that the rule for a rotation counterclockwise of 270 degrees is y negative x. The important thing for you to remember is it does not matter where your image starts at. This will always be the rule. So, for example, if we had started with our pink figure, and I said rotate it counterclockwise 270 degrees, it would then end up in quadrant 1. We're still going to follow the rule y negative x. So if you take any of the numbers in pink and apply that rule, keep your y and change x to the opposite, the point would be 2, 3, which is the image in quadrant 1.
So yeah, that's a very good point. These are the 3 rules no matter where you are. So we started out in quadrant 1 because that's the easiest to show you guys for the first time, but if you start anywhere else, the rule is not going to change. These are the 3 rules. So this is a very important piece to maybe memorize or draw something like this. These are your rules as well. This is a YX rule. This is an XY rule. This is a YX rule. And then the signs go into place for them.
The important thing to remember is that every 90 degrees they're going to flop places, and then once you flop their places, and you know where the image will end up depending on how many degrees it rotated. And based on where it's ending up, you should know the signs. So rotations are actually pretty easy once you get the hang of them.
If it's actually, for me personally, if it's not asking you for a rule, I don't even use the rule. I just know every time I go 90 degrees, I switch my X and Y. So if I am starting here and I go 90 degrees, I just know whatever this is, my X and Y need to switch and it's going to become this.
Yep.
If I know I'm going from here 180 degrees, this point up here, R prime is going to go X, Y. I'm sorry, whatever here is going to be YX and then XY right here is my answer then.
So you'll flop twice.
So unless it's asking for the rule, just remember every time you switch, or every time you go 90 degrees, you switch X and Y. That's all you really need to remember.
Excellent.
All right, so that is the conclusion of this lesson. Hopefully you feel pretty confident about rotations and being able to describe them in numerous ways. If you have any questions, as always, reach out to Miss Netz, myself, or your teacher if it's not one of us.
Hey, Mrs. Michael.
Hey, what?
Which triangles are the coldest?
Which triangles?
Isosceles triangles. Get it? Ice.
I get it.
All right.
Thank
we
you
will
so much.
see you in the next lesson.